Welcome to POGL Activity 24, and this is called Reactions of Carboxylic Acid Derivatives. So the goal here, the objectives of this activity is for you to recognize and classify the different carboxylic acid derivatives. So we're going to learn that. What is a carboxylic acid derivative? We're also going to, another objective is to learn what kind of reactions these carboxylic acid derivatives undergo, and that's called nucleophilic substitution. So we're going to undergo nucleophilic substitution reactions, and then we're going to actually do that. It's actually nucleophilic substitution, and we'll put in the word acyl. So nucleophilic acyl substitution. And we're going to learn their different reactivities. So you're going to learn the different reactivities of these different carboxylic acid derivatives. Because you'll learn that certain carboxylic acid derivatives can convert through nucleophilic acyl substitution into other carboxylic acid derivatives. Some of them cannot, though, however. And so that is what we'll be doing. So first of all, let's work Model 1. And Model 1 shows an R group, so that's any kind of carbon. And then we have a carbonyl. And then we have a lone pair on the Y, and this is called your carboxylic acid derivative. And then in general, the structure of the carboxylic acid derivative, Y, is any atom that contains at least one pair of electrons. So let's do question 1. Consider the carboxylic acid derivative shown in Model 1. Draw 2 additional resonance forms for the carboxylic acid derivative. So when you do this, put in your lone pair on the oxygen. You have 2 lone pairs, and then you have your Y. Now the resonance structure here, this is there, and then that goes to there. There's your resonance. And so that gives carbon. No, not a positive here, because it has a double bond. The positive is going to be on the Y, because you have a neutral species here. You have to have neutral here. Now, so the hybridization of your carbon, oxygen, and Y would be sp2 because it participates in resonance. I guess another resonance structure could be if you wanted to keep those electrons on the Y here, and that would give the carbon a positive. So there are 2 additional resonance structures. Draw the resonance forms of a ketone. Okay, well, a ketone would be something such as this, and your resonance structure would be a negative on the oxygen and a positive on the carbon. Compare the resonance forms of the carboxylic acid derivatives to the resonance form of the ketone. How are they different? Well, on your carboxylic acid derivative, you have a lone pair of electrons on the Y atom that can participate in resonance. And in this case, that gives you an extra resonance structure. So you have one extra resonance structure. Which atom in the carboxylic acid derivative would act as the electrophile? So here you could say it's the carbon, right? The Y could as well. Electrophiles have the positive. Consider the Y group on the carboxylic acid. A Y group that donates, so this is donating these electrons, donates electrons would make the acid derivative a more reactive electrophile. Because you would have would it be more? Okay, not sure. Sometimes Pogue will ask questions and I'm not always sure what it's going towards. Let's go on to question number 2. I do think the questions are good though. It makes you see details. Identify which of the following are carboxylic acid derivatives by circling the Y group in each compound. Put an X or any compounds that are not carboxylic acid derivatives. So if we were in class, we would put these all on the board and have different people come up and determine whether we have carboxylic acid derivatives or not. Now you notice I'm putting in my lone pairs. I would recommend that you always do that. The way you problem solve in organic chemistry is always you start with a correct Lewis structure, and Lewis structures have lone pairs. So just because they're not given to you doesn't mean you do not put them in when you're problem solving. My goal is to teach you how to problem solve. Okay, so here we have, let's find our carbonyl. Here's our carbonyl. Carbonyl, 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 carbonyl. Now what we're looking at is the Y group. So I've circled the Y, and then we've got to see if we have a lone pair, okay, on that atom. So do we have a lone pair here? We do. So this is a good one. We have a lone pair here, so this would be a carboxylic acid derivative. We have a lone pair here. This is an amide, and it would be. And this is an acid anhydride. It would be. What would not be is the ketone. Let's go to Model 2. Model 2 is called nucleophilic substitution of carboxylic acid derivatives. So now when we add a nucleophile, you see that our product, the nucleophile adds, and the Y is a leaving group. So let's read question number 3. Consider the reaction shown in Model 2. What is the role of the carboxylic acid derivative? So here's your carboxylic acid derivative. And if this is a nucleophile, it is an electrophile. A nucleophile reacts with the carboxylic acid derivative. What is the leaving group? Y is the leaving group. If Y is a strong base, the reaction would proceed in the forward or the reverse direction. So let's look at carboxylic acid. So this would be, and so if you had a nucleophile here, then you would get OH minus. And we know that that's a strong base, right? That is a horrible leaving group. So it's not going to want to go this way, it's going to want to go here. So reverse. Okay, because if this leaving group is a horrible leaving group, then it's not going to want to leave. So it's going to, so OH is an example of a horrible leaving group and it's unstable. So what if Y is a weak base? So let's take something like this, which this is an acid chloride. And so when your nucleophile adds, you get the chloride, and the chloride is a weak base. And you know that because HCl is a strong acid. It's a very strong acid, right? And so its conjugate base has to be a weak base. That's the principle. And so in that case, the reaction would proceed in the forward direction. So if Y is a weak base, the reaction would go forward. In your groups, discuss how the basicity of the Y, affects the reactivity of the acid derivative. So acid chlorides are very, very reactive, folks, okay? Very reactive, very reactive. And that's because chloride is a weak base. It is an excellent leaving group. Carboxylic acids are very not reactive. They're not going to be very reactive. And that's because OH is a strong base and a horrible leaving group. Let's go to question number 4. In the following table, so let's fill out the table. You have an acid derivative. You have a leaving group. We have a pKa value. And we have a reactivity. So the first thing we have is an acid chloride. And I'm going to draw it out for you. The next thing we have is, and you can write the names down, this is an acid anhydride. RCO2COR. So this is acid chloride. These are functional groups. This is acid anhydride. We have an ester. You all have seen esters before. And we have an amide. Now, we also have pK values, -7, 3 to 5, 16 to 18, and 38 to 40. So you see we're increasing those pKa values. Draw the appropriate leaving group. So they want you to draw this leaving group for each acid derivative in the table. So here it's the chloride, and it takes the electrons. Here it's the acid anhydride that takes the electrons. Here is the ester. Here it is the amide. And notice it takes the pair of electrons. Based on the pKa values given, Which group is the most basic? Now these pK values, just so you know, this would be like HCl because it's an A for the acid. This one would be the carboxylic acid. So that proton there, 3 to 5. This one would be your alcohol, so 16 to 18. And this is amine. So if you have a hydrogen on a nitrogen, it's typically 38 to 40. Excuse me. Okay, so what does it say? Based on the pKa values given, which Y is the most basic? So strongest acid, weaker conjugate base. So the Y that we're talking about is the most basic. Which Y group is the least basic? So this one here would be the least basic, leaving group. Rank the acid derivatives in the table below from 1 to 4, with 1 being the most reactive. So this is number 1, the most reactive. This is going to be number 4, the least reactive. So this would be number 2, and this would be number 3. Once your group has reached an agreement, discuss whether your conclusions agree. Now, I'm going to tell you, I've spent some time in the lab having to convert between these different acid derivatives when I did organic synthesis, when we were doing drug design. And so a lot of times if I started with an acid chloride and the reaction was just too reactive, too quick, sometimes when that happens, you don't get the best yield and you want to be able to control it more. I would always switch to an acid anhydride. And that usually would allow me to do it more like room temperature instead of a cold reaction and maybe let it go overnight rather than had to work something up in 15 minutes. And then if the acid anhydride was too reactive, you can go to an ester. Yeah, I never used an amide. People do not want to convert amides into other things. Let me just tell you, amide is at the end. You convert things to amides, but it's really a pain to go from an amide to anything else. All right, now we're ready for Model 3. Now, Model 3 is the reaction mechanism. This is a reaction mechanism when you're dealing with acid derivatives. And they, just like when we do elimination, E1, E2, SN1, SN2, free radical substitution, this one is nucleophilic acyl, so that means there's a carbonyl there, substitution. So we are substituting the Y group, the leaving group, with a nucleophile. Okay, so whatever nucleophile reacts with our acid derivative, we're going to substitute the Y for that. So in the reaction of carboxylic acid derivatives, the nucleophile can be either negative, which means a strong nucleophile, right? Or it can be neutral. And neutral would be a weak nucleophile. Substitution occurs because Y is a leaving group. You've seen this with the Grignards, with the esters. The mechanism, it always occurs via tetrahedral intermediate. And I want to see that, folks. Okay, so we're going to go through a tetrahedral intermediate. You've already done this with the esters and the Grignards. So this is kind of review, but now you're really looking at it. Okay, so you're going to take a nucleophile and you're going to go through a tetrahedral intermediate, which means that carbon is bonded to 4 things. And then you replace the Y group, the leaving group, with your nucleophile. And this is your tetrahedral intermediate. So let's answer our question 5. For the reaction shown in Model 3, draw curved arrows to show electron movement for both steps in the mechanism. You will have to do this, okay? So you always draw from the nucleophile to your electrophile, and then those electrons go on to oxygen. Make sure you draw all your lone pairs in here, and now you have the nucleophile bonded here. This is your tetrahedral intermediate. And then in order to form your product, these reforming of the carbonyl is a very energetic process, and that's why the Y group leaves. And so those are your 2 electron flow arrows for each step. So there's 2 steps in here. When you see this, this is step 1 in the reaction mechanism. This is step 2. Why is intermediate called the tetrahedral intermediate? Well, this carbon hybridization is an sp2. Now here, it's an sp3. And then in your product, it goes back to an sp2. So it's sp3 hybridized carbon. What other similar reactions forms the tetrahedral intermediate? You did that with the Grignard. So when you did like methyl magnesium bromide to a ketone or an aldehyde. So you took this nucleophile, you added that, and this made a tetrahedral intermediate. And then you protonated it with a little bit of acid to make your alcohol. In this case, you have an aldehyde, so you made a secondary alcohol. So aldehydes and ketones. How does leaving group ability affect the reactivity of the carboxylic acid derivative? So the better the leaving group, the increase the reactivity. So the better the leaving group, the faster the reaction. The reactivity is going to happen. From the table shown in problem 4, rank the leaving groups from the best to the worst. So if Y is Cl, that's your best. And then you had the acid anhydride. And then you had your ester. That was your ester. And then the worst was the amide. How do pKa values relate to leaving group ability? Okay, so this has HCl has the lowest pKa, and it's going to be your best leaving group. Okay, so the amide has the highest pKa value, between 38 and 40, and it's your worst leaving group. Does the ranking of leaving groups agree with the rankings of reactivity of acid? Sure, yes. Okay, number 6 is a good question. Let's make sure we can do number 6. Complete the following scheme by providing the nucleophile needed to accomplish each reaction. Draw the nucleophile above the arrow. So here we have our Y leading group, and here we're going to make an anhydride, and I call that an acid anhydride. Here you're going to make carboxylic acid. Here an ester. Here an amide. So what nucleophiles would you have to add for the Y to leave? This one would be this group here. This one, you'd have to add the OH. This one, you'd have to add the ester. And this one, you'd have to add the amide. And those would be the nucleophiles in order to make those carboxylic acid derivatives. Let's do Model 4. Model 4 is the reaction of an acid halide. There is a typo in this, so it should just be an acid chloride here. So it shouldn't have a hydrogen there. This is an acid chloride. I'm going to tell you how to make them here too. How do you make an acid chloride from a carboxylic acid? This is a reaction you're going to need to know. So here's your carboxylic acid, and if you react this with thionyl chloride, I usually use some pyridine. Okay, so pyridine, thionyl chloride, you've seen this already. You did this when you were making, like from an alcohol, you reacted these reagents and you made an alkyl halide. Okay, so this is going to make your acid chloride. And then the pyridine, actually, pyridine doesn't have the hydrogen, but it will soak up this hydrogen and this Cl to make pyridinium chloride. So it's a proton sponge, and it just keeps this reaction going. But this is how you make acid chlorides. Acid chlorides can be converted into everything else, and that's why it's important. So if you react an acid chloride with water, then you're going to get the carboxylic acid and HCl. And that's what they're showing you. If you put in pyridine here, it will become pyridinium chloride. So question number 7. Identify the nucleophile and the electrophile in the first step. So this is your nucleophile, the water, and the acid chloride is your electrophile. The nucleophile is, if you say weak, there's no negative charge, so it's weak. Draw the structure of the tetrahedral intermediate that is formed after the first step. So these electrons will come here on the oxygen from your nucleophile to your electrophile, and those electrons go up, and you will form a tetrahedral intermediate. So there's your tetrahedral intermediate. It's important when you're doing these intermediates to make sure you draw your lone pairs. Draw curved arrows to show electron movement from the first step through the tetrahedral intermediate that gives to the product. So these electrons, what I would do here is I would show the pyridine deprotonating, and I would show that going there, and then I would redraw for my mechanism. I would redraw this. And then I would show that these electrons come here and that leaves to give that carboxylic acid. HCl is formed in this reaction. Discuss the purpose of adding a weak base like pyridine to the reaction mixture. So we've talked about that before, and it acts as a proton sponge to absorb, to deprotonate, does the deprotonation, and since you're also generating the chloride here, it kind of just soaks up that HCl. Draw the product expected if you had CH3. So what if you reacted this with an alcohol? So if you had the acid chloride with methanol, what would you get? And you should be able to draw this reaction mechanism. Nucleophile to the electrophile. Those electrons go up to make a tetrahedral intermediate. You have your oxygen here. And now you want to do pyridine to deprotonate. That's going to become pyridinium. And the chloride will pick up and kind of hang out there because you want to redraw this for your reaction mechanism. So you have this tetrahedral intermediate. And then those electrons will come here, this leaves, and now you have made an ester. So this is an ester. So you went from an acid chloride, you react this with methanol, you get an ester, and this is a methyl ester. Consider the reactivity of the acid halide from question number 4. The acid halide is more or less reactive than the ester. Okay, so it's going to be more reactive. The acid chloride is going to be more. It's going to be the most reactive. Given the difference in reactivity between the acid chloride and the ester, would you expect the ester to react with sodium chloride to form an acid chloride? So would this react with sodium chloride? So would chloride displace the OCH3 for a leaving group? No. Okay. So this is a weak nucleophile. The nucleophile used in the reaction of acid halides must be weak. That's true. Okay, so you want to use weak nucleophiles, just like this. Given the reactivity of the ester compared with the acid halide, discuss whether the ester would be reactive with a weak nucleophile such as water. Okay, and it's not going to be as reactive with water. So you can use water with acid chlorides, but you're not going to be able to use water with an ester. If you want to do that reaction, it's called saponification. And so we've talked about this before. So if you have something like this, so you have an ester and you want to do saponification, then you want to use sodium hydroxide, right? And then that's a strong nucleophile. And you actually add some heat there, and then you can get this. Sometimes if you, and I don't want you to do this at first, but you can combine, but don't do this in my POGL, okay? I want you to draw it out and draw those steps. But when you're just learning after you've, this is a shortcut, and it's an accepted shortcut, where you have this double-headed arrow, and it means that the electrons go up and then come down and this leaves. But for you, there's too many electron flow arrows going on. So when I ask for reaction mechanism, I want you to draw out the different steps. I want to make sure you know how to do that for this class purpose. So this is saponification. So if you have an ester, you would have to use a strong nucleophile. Now, you have additional questions. You need to draw on your different products. You have to decide whether you need acid. Acid will make your acid derivative more electrophilic. So you will need to use acid for weak nucleophiles. But you can add that. 11, I expect you to so draw that out. And 12, that is a biological triglyceride. So it's kind of a good learning opportunity. And that concludes POGIL Activity 24, Acid Derivatives.